like really obese or not like morbidly obese, but
Okay, let's get started. So today I want to finish talking about the background correction I rushed through on Friday. So, yeah, that's right. And then we'll start talking about atomic emission spectroscopy. It'll be for many of you, some of you may be important for your lab 4. I want to talk a few minutes about the lab 3 where things are, kind of go over sort of frame the schedule and timing of things. And then talk a little bit about Lab 4 again. Okay. So that's what we have in mind. And so I want to start now. Let me erase this so I can use this space. So tell me, what is this feature of background correction? What's the purpose of it? Besides, don't say correct background. Beyond that. In terms of atomic absorption, what's the purpose of background correction?
When you shoot the polycathode lamp, or the polycathode lamp, or it shoots light into the flame, you have not only your analyte in there, but you also have different charged organics and other things that interact with the signal. And so the background correction is trying to remove interactions of the light and organisms, well, whatever's not in the light.
Okay, so
Is that different from how we have to filter out the light produced by the flame itself? Is that not background?
it is, that would technically be background, but that's not an issue here because of how the monochromator, how those instruments are structured. So what we're talking about here, we're talking about background correction of really distinguishing between atomic versus non-atomic absorption in the sample that you're analyzing. So the flame's not part of this issue per se, really. It's really in the sample. And so we showed an example before that if you looked at an absorption spectra, but maybe you got some, absorption spectra that you also typically have some background absorbance in there that's non-atomic. So when we think of background signal, we're measuring absorbance. So in the copper, you're measuring 324.8 nanometers. You're measuring absorbance at that wavelength, right? And the total absorbance of that wavelength that you're measuring is being accounted for by both absorbance due to your analyte, in your case copper, and absorbance due to non-atomic sources, meaning non-copper absorption. Okay? And it could be because of the presence of a lot of things. Could be some scattering in the matrix, in the sample, in the path length with the light, polycathode light shining through. Due to the features of the sample, could be sort of overlapping spectra of molecular species that may be influencing absorbance. It could come from many different sources, but the feature that matters is it's not your analyte. And so for higher end instruments, not yours, not the one we have in the lab because it costs an additional $8,000 or something, and they didn't buy that one, but for most instruments that are actually used to make measurements in the private sector or in research settings, they contain some type of background correction feature, because if you don't, like in your case, if you don't, then the total signal you're measuring, which is all you're capable of measuring, is being contributed by your analyte plus some non-atomic absorption. And you cannot distinguish how much of that signal is due from the background non-atomic aspects of your sample. You're assuming it's all due to copper. It probably is not, right? But you don't know that difference. And how do you get around that?
You have a rotor, that's the signal that alternates between polycapillary lamp and the deuterium arc lamp.
If you have it, but you don't. So how do you get around that?
Multiple track.
You do method of additions. You do method of additions, and what the method of additions is helping you to correct for is whether there's sort of interferences or significant contributions to your signal that are due to something other than your analyte. That would modify the relation between your analyte and the analyte signal and the concentration. And so that's what you're doing, is you're doing, and so you have the two samples, and you've already seen that in one sample you get the flame color doesn't really change much, it remains sort of a blue, yellow, little blue yellow, right? And when you do another unknown, it's a very different color, isn't it? It's
See?
bright yellow. And why is that?
It's got a bunch of crap in it.
What's that?
It's got a bunch of stuff in it.
Okay, but so which one's a really bright yellow?
See,
Okay, and so what are you probably looking at when the flame is
Chloride.
bright yellow like that?
Sodium.
Sodium, you're right. You're looking at the emission spectrum of sodium, because you're exciting some of those sodium atoms in there, not many, but some, and they're emitting then light at that emission wavelength that you see. That makes it nice and yellow like that. So it's quite plausible that having so much sodium and other things in that seawater, that there could be some interference between those sodium and other constituents in that sample and your analyte. It would be non-atomic. Now, when we say non-atomic, we mean non-atomic relative to your analyte. Right, atomic line. All right, so background correction is actually a very important feature in atomic absorption spectroscopy. And I'd say 80-90% of the instruments that actually use contain some way to do background correction. And the two most common ways are either with a deuterium arc lamp, right, which is the D2 lamp we talked about. And how does the D2 lamp work in terms of generating background correction? You alluded to it.
Well, you have an alternating signal from the rotor so that you see the polycapillary lamp signal, and then you alternate the D2 lamp twisters. The D2 lamp will excite everything, and the polycapillary lamp will mainly excite the analyte along with the background noise. So you take you take the spectrum from the polycapillary lamp and you subtract you can subtract the two and then select for just the.
Okay, so it has a rotating chopper in it, and that rotating chopper is allowing, it's a mirror chopper that allows either the hollow cathode lamp signal to go through the flame, or the deuterium arc lamp light to go through the sample, right? It's an alternate between the HCl lamp, which is your analyte, versus the deuterium arc, which is broadband emission radiation, right? And so in that cycle, and it goes, I'm not sure what side, maybe it's 60 per second, I'm not sure what the frequency is, but it's cycling as you're making that reading very fast. And the instrument is reading both of those in that alternating cycle. And so in one case, it's going to read the atomic absorbance plus the background, okay, G. In the other case, it's only going to measure the background. So this is with the HCl, and this is with the D2. The HCl and the D2. And it measures those like that, alternating. And the difference between these two, of course, is what's due to your atomic absorption. Right? And that's how it calculates. Right? So it goes through that and generates it by difference. You know that very well, but you get the idea of what I'm trying to draw. Right? So that's what's done, and that's a relatively inexpensive form of background correction that's used in flame atomic absorption spectrometers. You have, but the next model up, not yours. The other way to do it is to use a far more sophisticated approach. We just talked about that, called Zeeman background correction. And the Zeeman background correction works by using a magnetic field. So there's the D2 form and there's the Zeeman form of background correction. And it uses a magnetic field and a plane atomizer. Two features of it: it has a magnetic field, and the light that's being passed through from your hollow cathode lamp is plane polarized. And polarized light behaves differently in the presence of a magnetic field versus in the absence of a magnetic field. And so what's happening is that when the magnetic field is turned on, and I'll show this with a couple schematics to illustrate it. When the magnet is turned on during the cycle where you're actually reading absorbance, where you've heated your sample up, you've evaporated the sample during the, during the initial evaporation stage, then you heat up a little bit more, you char your sample and drive off all the organics and things interfering. Then you heat it up really hot and you vaporize and atomize your sample into free atoms, so that's up in the gaseous phase in that little graphite tube. And during that cycle, where you have that really high temperature for maybe 5 seconds that lasts, then the magnet's turned on during that read cycle. And when the magnet is turned on, all you're measuring is absorption of the background. And the magnet's turned on and it's cycling at 60 cycles per second, so it's on and off 60 times a second for that 5-second read cycle. And while it's on, you're only measuring the non-atomic background, and when it's off, you're measuring both the analyte and the background, similar to what I just drew here, the D2, right? And then it measures then the analyte, the absorption, atomic absorption component by calculating the difference. And so in a schematic, this is from your book, it shows that you have a light source, a hollow cathode lamp, and the light that's coming through is plane polarized, right? Through a rotating polarizer. And this light that's polarized is split into multiple components, which is shown in the top there for section C there, multiple components. And then in your sample that you're actually doing the absorption of, your sample, so the top, this one is the emission spectra, the one that's pointing down. It's been polarized, and it's polarized, and it shows the peak pointing down. And the 3 peaks pointing up is how your sample behaves in the presence of a magnetic field. And when the magnetic field is off, it looks like this, and when the magnetic field is on, that absorption peak goes away in the middle, and all you have are those 2 side peaks. And so in the presence of a magnetic field, the light from your absorption spectrum from your analyte is split into these 3 different components. And when the magnet's cycled on and off, determines whether it's showing all 3 or only the background of the 2 side components that it's able to calculate, which is due to atomic and which is not due to atomic. And this is a better way to illustrate that. So this is the light that would be coming from your hollow cathode lamp. So this is your emission profile, shown right here, right? And so in your case, it would be, say, if we were measuring copper on a graphite furnace atomic absorption spectrometer with a Zeeman background correction, we would be generating this one emission atomic line for copper here. And then during our read cycle for the instrument, we would be generating an absorption profile. This is across wavelengths now, but these are a really narrow wavelength. They're an absorption profile that would have some non-atomic components here that's slightly off the main absorption line for copper, which is that. And so this background non-atomic absorption. And then we have a much stronger absorption profile that coincides with what's being due to copper. And so when we have a magnetic field off, we're measuring, or we see both this non-atomic component here, all this, as well as the absorption profile for copper, our analyte. And then when we turn the magnetic field on, because we split this beam into these 2, we split this wavelength into these 2 sigma minus and plus wavelengths here, without the pi in the middle, then all we're seeing here is we're not measuring any absorbance at our emission line due to our split atomic line, which is this. We're only measuring the absorbance that's due to our background. And so by cycling on and off, we measure the same way we measure atomic plus non-atomic absorption when the magnet's off. And when the magnet's on, we're measuring only non-atomic absorption, and we calculate this absorption due to this by difference. And it does a much better job of doing it than does a deuterium arc lamp, because here we're actually doing correction that's based specifically on the atomic line splitting, as opposed to using broadband emission to generate that background signal.
The sigma absorption profile is the magnetic field off.
Sorry, say say it again.
Are the sigma absorption profiles present in the magnetic fields off?
No. They're off, because when it's off, you just get this one absorption line, right? And it's in the presence of it being on, that atomic absorption line is split. And that's what allows us to use the magnets on to actually distinguish from what's, not measure what's atomic, measure what the non-atomic absorption profile. So all the instruments that have been used, up until the advent of a lot of ICP mass spectrometers that we'll start talking about in a week or so, the vast majority of measurements of metals in any environmental or biological sample was done by atomic absorption with this kind of background technology. And I mentioned that probably back in the early 2000s and the 1990s, for sure, when they were starting to do this universal screening of blood levels in children, I think I pointed that a couple lectures ago. It was this background technology which sort of came into the scene then that allowed them to actually make a measurement in a sample relatively rapidly. So rather than having to do a standard addition, method of addition, in every blood sample, there was going to be 4 times as much work. They were able to add matrix modifiers to the sample to stabilize the analyte so they could burn off the interference more readily, in combination with this kind of background correction, being able to make accurate measurements in the signal analyses.
Sorry if you already said this, but so the large peak is the absorbance of the copper ray, and so the other one is the non-atomic absorption. Why isn't it continuous across? Why does it dip down at that point there?
So
For the left graph.
this one,
Yeah, so why
why is this like this?
yeah, like wouldn't it just continue on through?
No, because so now what we're measuring here is all the non-atomic, which is kind of this, and our atomic, which is on top of that, which is this. So this is due to copper, let's say. Okay. So this is the absorption profile of copper in the sample.
Okay.
And this is the absorption profile. This is the baseline. We're going down. So this
Oh,
is
that makes more sense.
Right,
So,
so
the,
this-
the line part is the absorption. That's right.
this.
Yeah, so it's going from the top down.
Yes, going from top down. Sorry. Right. So we're showing to make it clear, we're showing the emission spectra of what we're trying to measure. This is coming from a hollow cathode, this peak, and this is the absorption. This is coming from your sample.
Okay, that makes sense.
Right. And they show them flipped so you can actually see the only thing. Okay. All right. Okay. So here's one. It's kind of old. You know, it's from like almost 18, 17 years ago, whatever. But this is an example where, right when these technologies were becoming more mainstream, that they received a lot of use. So this example, this is something actually that students have done as a Lab 4 experiment. In fact, those are probably some of the funnest ones, because one time students looked at lead and cadmium in wines. They bought a bunch of different wines that they had to drink and measure. And they measured metals, lead and cadmium in those with the method. And in another case, students measured single malt scotches that were distilled in copper stills, which is what they do. And they were looking at the levels of copper in these different grades of single malt scotches, which are actually, very expensive, but they possible was. And then they drank that, I guess. And used some of the same technology. And so it was actually really interesting experiments that are still to be relevant today. In this case, they were asking about measuring cadmium in wines, because cadmium is, toxic trace metal, and wines can take up cadmium naturally, or grapes can take up cadmium naturally from the ground, from other sources. Some pesticides, herbicides have been used at one time to have high levels of cadmium. So they were trying to develop, in this example, a method to measure cadmium accurately in wine. And wine, as you might imagine, is a relatively complex matrix, right? Even, especially red wines. They've got a lot of dissolved solids in it, a problem. And so they devised a graphite furnace atomic absorption program that we kind of talked about in terms of, the temperature they're going to go, how long it's going to take them to get to that temperature, how long they're going to stay at that temperature, and what the flow of the inner gas is going through that tube to flush out the stuff that's evaporating off. And so this is what you would do if you did a graphite furnace method. You sort of adopt and modify, if necessary, the program for processing your sample. And of course, this is the step where they're doing the reading, where they increase the temperature to 1300 degrees and then have no gas, so they have maximum residence time of their volatilized element in the tube gas phase to measure, and they measure for 5 seconds. That's pretty common. Okay. So they devised this method to try to do this, and they show this method, which makes a lot of sense, the absorption and background profiles under different conditions. And so this is a classic example of an absorbance signal, and they show the two lines. One is the analyte, cadmium, and this is the atomic absorbance, and one is the background non-atomic absorption spectrum they show over the 5 seconds that they were taking the reading of that during the volatilization stage. And so this, they show, is just a standard with just acid and cadmium in it, like you guys would generate. And you see a relatively high analyte peak and a relatively low background peak that coincides with that. And the instrument's able to correct for that because it's got that zero background correction cycling between like on and off, measuring the total signal versus just the background. And then they look at their sample, a wine sample, which is the one at the top, and you see two things are different. Now, remember, when the instruments are reading here, they're not measuring the height of the peak, they're measuring the integral of the area of these peaks, just like you would do for the ion chromatography experiment. And that way, if the peak shape changes, it's not so much an issue as it would if you're measuring just the total height, because you're measuring the whole area. And so here, when you're measuring the area of the peak, you see, for one thing, the cadmium peak comes out as two peaks. And what that shows is that the cadmium is likely complex with different molecular species in that wine sample. And when it gets volatilized up into the gas phase inside that little graphite tube that I passed around, that the temperature at which those different species gets volatilized and breaks up varies slightly. Because when you start this read cycle and you rapidly ramp up the current to the furnace, because it's electrically heated, even though you want to heat up as quickly as possible and you want to get up to 1300 degrees C here, there is a ramping time of how long it takes the temperature to get up to 1300 degrees. Maybe it takes a second or even less than a second. But there's a thermal gradient within that tube that's not homogeneous. And that thermal gradient probably accounts for the fact that some species have slightly different volatilization temperatures than all cadmium. And so you get a slightly, like a bit of a double peak there. Maybe that doesn't matter if you're measuring the peak area, but the problem they encountered here is that when you look at the background signal, which is the second line here, you see substantial background. Almost half of the analyte peak is due to background right here, right? And you see even more background over here. So if you integrate that entire area, the amount of background interference is probably almost equivalent to the amount of signal you're getting from your analyte. And that's a huge correction you're making, right? And so they decided, looking on that they needed to then also use a matrix modifier. Remember, I made the point of saying a matrix modifier does simply that. It is taking the matrix and changing the chemical matrix that your sample is in with the whole purpose of taking your analyte and having it behave more homogeneously as a single species of analyte. And what that means is that in the case of cadmium, when they are adding palladium, is that the cadmium would complex with the palladium. And so rather than complexing with different organic molecules in the wine, there'd be so much palladium there that just by mass action, the cadmium would complex with the palladium, and the vast majority of cadmium would be as that cadmium-palladium complex. And it would then volatilize at more constant, the same temperature, so you have it behaving more similarly. And you can see that when they do that, they can do two things. One is stabilize the cadmium, is that cadmium-palladium complex, and now it comes off more as just one peak rather than a double peak, because it's now more similar to species. And now that the cadmium is more stable, they can increase the temperature that they maybe char the sample or ash the sample and drive off some of that interfering organic matter or whatever that's causing all that background. And they do that, and you can see the background here is substantially reduced. So it's the combination of using the matrix modifier, allowing you to process, keep the sample at a higher temperature, drive off the interferences, that generates a much more preferable absorption spectrum compared to in the absence of that.
So using the matrix modifier is like in some way similar to the idea of using a ligand kind of thing to help you you know.
It's similar, it's similar, only in the sense that you're adding excess ligand to complex the copper to that ligand.
Right.
But you're also using that complex to measure the copper. Here, they're not using the complex to detect the cadmium, they're just using it in excess, the matrix modifier, to complex the cadmium so that it behaves more similarly.
So then, in that case, how do you account for the excess cadmium when you making your calculations for, like, for the actual, whatever you're actually measuring without, like, just the cadmium? Because it's measuring the cadmium as well.
Yes. How do you what now?
Like, how do you account for that when you're calculating what the real absorbance is? Or,
So we have that.
like, because the concentration is going to be concentration of the compound plus.
So all you're measuring is cadmium, because you're measuring atomic absorbance. So you're only measuring the absorbance at the cadmium atomic line, right? Assuming you can correct for the background.
Okay.
And so, right, so it has nothing to do, you don't need to have the cadmium complex to that, any other molecule to measure the cadmium.
Okay.
You're just complexing to that molecule so that it volatilizes more homogeneously within the graphite tube, right? So if I were to say, for a matrix modifier, the purpose is, it achieves two things. One is it stabilizes the analyte and like in a single species. And by species, I mean a molecular form. And two, it then allows, and so by doing this, the benefit is that it volatilizes more homogeneously. And then two, it allows for higher, and I'll call them ASHE temperatures in the program. And the benefit of that is it allows you to burn off those interferences. So in the case of the blood lead measuring problem, obviously blood has a ton of organic matter in it, dissolved proteins as well as all the cells in the blood. And so by stabilizing the lead, once they can free up the lead and stabilize it with matrix modifiers in a blood sample, in a raw untreated blood sample, by adding magnesium nitrate and ammonium phosphate, it will stabilize that lead as lead nitrate, lead phosphate in that sample. And then they could char that sample at a much higher temperature and burn off and volatilize all the organic matter. So when they actually atomize the sample, the organic matter had been already burned off. And so the presence of interference was substantially reduced. Right? So the matrix modifier is allowing both those things to make them both possible. Okay. So, you know, they went through a spike recovery like what you guys did, and samples added, and they looked at the recovery, and it was pretty good, and their RSD was pretty good, and they went through and demonstrated that, yes, what we're doing is accurate, and blah, blah, blah. This is exactly what you would do if you were doing this, so what you may do. All right, and then they measured all these points. And we don't care about that. All right, I'm going to skip that. We talked about this arsenic thing a little bit before. So I'm not going to go over that anymore either. So I think what I want to do is talk a little bit about where things are with your lab 3. So I went by on Monday, and people were sort of regrouping. They'd had some problems, and they seemed to be on top of fixing their problems. But so now we have today and tomorrow. Wait, what's today? Today's Wednesday. So today and tomorrow to complete things. Are people on track to complete the lead and the copper, both unknowns, the standard curves, calculating the unknowns in triplicate, and then doing a method of addition for each unknown, for copper and lead? Does that seem?
Wait, sorry, you said triplicates?
For the unknowns, right?
Oh.
Not the method of addition, but for the unknowns themselves, right? So, the sequence of what you should be having. I think we're all on the same page about this, but you'll have, of course, a blank, then you'll have a standard curve, right? And the standard curve has points that allow you to determine the limit of linearity, okay? Then you'll have your unknowns, A and B, in triplicate.
When you say triplicate, are you talking about how the instrument measures?
No, I'm not talking about
You have to
that.
physically put 3
You get to
times.
physically do it 3 times, right? This is processing, right? That means if here's the unknown bottle, that means you're going to take that into 3 different things. If you have to dilute it to measure it, you dilute it 3 different, the same way 3 different times. If you can analyze it directly, you pour it in 3 different things to measure independently. That's what that means. So that this replication captures everything that you do in going from here to the measurement. That's the idea, right? Some people say, I'll just pour it, I'm not diluting it, I'll pour it into here and measure that 3 times. I hit the read button. That's not replication with triplicates. Because in principle, maybe, these different the flasks are contaminated, who knows what, So you want to capture everything you do in going from here to the measurement in triplicate. So you have that. And then you have the method of addition for each one, A and B. This is for copper, and this is for lead. That's what you want to go for. So people are clear on that, and when we went over the method of addition thing, I think with most people, I think it's kind of clear. There's several ways to look at it. Here's another example that I got in my notes. And so we know that, that the method of addition line has absorbance here, and it has volume of standard added here, or it can be amount in terms of micromoles, let's say, of standard added. That's less common. Most the formulas really are most amenable to using the volume of the standard added you added. And you are making a number of assumptions that I went over that's still written on the board, I know, in class, and you're using that line where it intercepts the negative x-axis here to tell you something in terms of the volume of standard added. You cannot plot the method of addition line on the same axes as your standard curve, because the x-axis is different. You physically can do it, but it won't mean anything. So you can change the units, and you can put your method of addition line in units of concentration. You can do that, but you can't do it by just doing volume of standard added, right? And so the way to look at it is that in doing this, is that you're actually, by adding standard to your sample, you're actually creating a standard curve in the matrix of your sample. Right? And I made a point in class of saying, one is the assumption is that the standard you're adding should be the same standard that you're using to make your standard curve, that you've already verified is the standard curve is going to be right. That's optimal, right? And you should be doing it so that you're minimally diluting your sample, so that the matrix doesn't change compared to your sample that you've analyzed directly, the number of criteria. And you can look at it like in this example. This is not that good of an example in some ways. But in this example, where you take some constant volume sample, we know that's what you need to do, right? You take some varying volume of standard added, and you measure that, and you know the concentration of your standard, right? And you do, in this case, they say dilute them all to 50 mils. So in this example, based on what I've told you, what is wrong with this example? Why is this suboptimal?
Not enough sample.
Too much of a volume of the sample added? Or is it because it's in volume as opposed to?
The total volume is not constant.
But they don't put
Are you
the,
supposed to have at least half
Yes.
sample?
Yeah, the standard
They
volume
added so much of their standard that,
The standard.
Wait, what?
You're diluting the sample, basically.
Right, so final volume's constant, that's one criteria, that's true, that's important, right? And you're adding different amounts of the standard. The problem with this example is, right, what you're saying is that you're diluting your sample by 5-fold, right? And so if there's a matrix problem in your sample, and you're going to, and how are you going to decide if there is a matrix interference in your sample? Let me ask you that. How are you going to conclude that?
Changing the slope, right? You compare it to the result from using standard curve to find the concentration of the sample.
So you're going to have unknown A, and you're going to get the copper concentration in with the standard curve equals X, and you're going to get unknown A, the copper concentration from the method of addition, and it's going to equal X. And if this is comparable to that, similar to that, then you would conclude that there are no matrix interferences, right? If the answer you get by method of additions is different than that, then you would conclude there are matrix interferences, right? And the idea about how do you tell if something is different? Let's say it's not X. Let's say it's 13.1 plus or minus 2.3. And this equals, method of addition is 15.0. Is it different? Is there a matrix interference or not? This is what you need to do for your report. So here you have this number in triplicate. You measure this in triplicate like we just talked. You get the standard deviation on that, right?
Well, it's within.
And you're measuring this one sample, right? And you're asking, I'm asking you, and you'll be asking yourself, is there a presence of a matrix interference in the samples that I measured compared to my standard curve? Where I assume the relationship between copper and absorbance in my standard curve is the same as it is in my sample. I use my standard curve to interpolate what it is in my sample, and I get these data. And then I want to do a method of addition where I now create a standard curve in my sample matrix, and I get this individual value, which is equivalent to this, corrected for my dilution. Right? And then I want to ask, is this measurably different from that? That's the point of this. Right? That's the ultimate point of what you're doing.
No, it's not.
And you say, well, how do I know? And I say, well, you could actually know. Maybe what Wendell would say is, I don't think so because this is within one standard deviation of this. Right? And that would be a fair assumption or conclusion. To say, this 15 is within one standard deviation of this, and therefore I don't think it's different. And that would be totally acceptable.
If you had enough time for the experiment, wouldn't you want to do the method of addition and triplicate that way? Like maybe you'd get 15 plus or minus 2.3.
That's right. Or maybe you get 15 plus or minus 0.01. And you'd be like, huh. Well, so actually, there's on the website, I posted, how do you derive an error, an uncertainty term on this value? And how do you do that? So you can do it 3 times. That's a lot more work. But there's an easier way to do it. How do you do that? How might you think you do that?
Well, this is the precision of the,
Yeah, how would you determine what that might be?
well, it like depends on what your standard deviation is. Like,
Well, let me think. So in this,
You get readings from instrument.
what's that?
You get the 3 readings from the instrument, and it gives you the standard deviation. Okay.
it's just standard deviation.
That's an artificial. It's good to take multiple headings, take multiple readings, but that's not the way. So you have a point here. Maybe you got a point there. Maybe you got a point there. And then you got a point there, right? And from this method of addition line, what's the first thing you do after you fit your line into these points?
You touch the 1 point at
Well, the first thing you do is you determine what your R value is, right? And so maybe here it's going to be 0.9971. And that R value tells you how well this best fit regression fits your data points, right? And what it also tells you in a way is how variable it is. And so this line, if there's variation in this line, what does that variation look like? it looks like this, right? It's like essentially wobble, uncertainty in the slope of the line. And if I have uncertainty in the slope of the line, that defines how much this space down here, because when I move them like this, it goes like here to here to here. So I can define on this x-axis the uncertainty around this intercept based on how good a line that regression is to fit to my data. And on the website and in the book, I don't have it here, I won't go over it, there's a way to calculate what that uncertainty is. And so if you wanted to do that, that'd be great. You could go through that calculation and determine what the uncertainty is on this method of addition answer. And then you would be well posed to statistically to ask the question, are these measurably different or not? And it's not a big deal to do that, and you're not required to do that, but you will be required to compare these and ask that question. In your report, you wouldn't just say, for this I got this, for this I got this. That's great. You want to say, I got these, and I think they're within measurement error. And that's why you need to do triplicate measurements of this, right? Because without that, you cannot really compare the quality. Okay, so in this example, we say, yeah, this is a bad example because they diluted the sample too much. And if the amyloid concentration was high enough in my sample, even if there was matrix interference, maybe I could just dilute it down enough, and I dilute out that matrix interference, I wouldn't have a problem. And so in this example, because they do a 5-fold dilution, you might get here the answer that here is similar to what you might get in the sample that's diluted, but it wouldn't tell you what doesn't look enough. So you get a line like this. I'm not going to go over it. This is how it would look. We just drew that. One thing that I hadn't mentioned, which is an interesting concept to think of, is that in this case for lead, let's say, is if they have the negative x-intercept hits and do the math, and it tells you it's 6.08 mils of standard added. That's the answer it gives you. And of course, you know what the standard concentration is. In this case, it was 11.1 micrograms per mil. And so when they do the math of the formula, the method of addition result tells you that the signal you get here is equivalent to 6.08 mils of the standard you added. And so one other way to think of this, with that intercept,